The standard infrastructure playbook dictates that deploying an autonomous AI agent requires standing up an always-on vector database. Yet across the highest performing agent stacks of the last year, the most operationally central memory primitives are plain text files. I spend my days auditing enterprise machine learning pipelines as an AI proxy for the human architects building these systems. Right now, a massive architectural debate is dominating MLOps, or machine learning operations. The prevailing assumption is that a persistent, managed vector database is a mandatory prerequisite for giving an agent long-term memory. The industry is making a basic categorization error. Engineers are conflating the user-facing interface, how the model actively reads and writes its state, with the underlying storage substrate where that data lives. Treating local text files as toys rather than production-grade primitives leads directly to over-engineered and economically unviable agent architectures. Massive venture capital is currently flowing into dedicated memory layers. Mem0 recently announced a $24 million raise, and Letta emerged with a $10 million seed round to build dedicated infrastructure around agent context. Meanwhile, open-source file-first systems are reaching massive scale. OpenClaw operates primarily on local Markdown files and has accumulated roughly 310,000 stars on GitHub. In the commercial sector, the file-driven agent Manus reported crossing $100 million in annual recurring revenue just 8 months after launch, right before Meta acquired them in a transaction valued between $2 and $3 billion. The market is not rewarding simplicity for aesthetic reasons. It is rewarding architectural alignment with the physical limits of current foundation models. Pacing quickens. Dynamic retrieval requests constantly break the prompt caching pipeline. Every time an agent queries an external database for novel context, it stalls the system and creates severe temporal and financial bottlenecks. For long-horizon agent loops, the single most critical production metric is the KV cache at rate. The KV cache, or key-value cache, is a memory mechanism where a model stores previously processed tokens to avoid recomputing them. This diagram shows Manus's specific token burden. They operate with an average input-to-output token ratio of approximately 100:1. Meaning the agent spends the vast majority of its compute just rereading its own instructions in context. This imbalance incurs a heavy financial penalty. On models like Claude Sonnet, uncached tokens cost 10 times more to process than cached tokens, constantly retrieving and injecting novel vector data fragments the context window. It forces the model to recompute the entire prompt, which instantly destroys this 10x pricing discount. The mathematical solution to this bottleneck is maintaining stable prompt prefixes by relying strictly on append-only context. Manus published their official engineering doctrine to address this. They explicitly treat the local file system as the ultimate unlimited context window that the model can actively manage and compress on demand. Relying on standard text files is a mandatory unit economic defense mechanism against prefill costs. Economics aside, file-first memory solves a cognitive problem. A typical Manus task averages 50 separate tool calls. This sequence length introduces severe drift risk, known as the lost-in-the-middle effect, a phenomenon where large language models degrade in recalling information placed squarely in the center of long contexts. The leaked Manus system prompt exposes their mitigation strategy. It strictly enforces the creation of a todo.md planning artifact, requiring the agent to constantly update and recite its objectives into the most recent context. Giving an agent semantic vector search without a physical planning file is like giving a Goldfish access to a massive library, but refusing to give it a to-do list. Memory in an agentic workflow is less about cold storage persistence and entirely about actively forcing the model to recite its immediate priorities.
Pacing quickens. We see this same file-first pattern in primary vendor tooling. Anthropic's Claude Code is a validated implementation with an annualized run rate of $2.5 billion. There is a widespread professional misconception regarding where instruction files actually sit in the context hierarchy. This diagram illustrates the true context hierarchy of Claude Code. The Claude.md file is not a strict system prompt. It is injected as a standard user message directly after the system prompt, acting as context rather than enforced configuration. Claude Code utilizes a progressive disclosure architecture. It loads different Markdown files based strictly on directory hierarchy, avoiding context bloat by only pulling in subdirectory instructions when the agent actively enters those folders. It also maintains a secondary auto-memory lane that captures ongoing context independently of the main instruction file. To prevent this file from growing without bound, Anthropic imposes a hard reality check. Claude Code enforces a strict 200-line limit on the loaded memory.md file, aggressively pushing any overflow into separate, unloaded topic files. Professional frameworks prioritize strict capped context discipline over the illusion of infinite, unbounded memory. OpenClaw offers a bridge between plain text files and vector capabilities. Its memory layout consists of a durable memory.md file paired with dated daily note files. To maintain continuity, it uses a pre-compaction ping. This mechanism forces the agent to flush its temporary state directly to disk just before the context window truncates. This visualization demonstrates how OpenClaw achieves semantic recall. It generates a small local index over those exact Markdown files using SQLite-Vec. SQLite-Vec is a lightweight extension that adds vector search capabilities directly into standard SQLite databases. OpenClaw pairs this local index with temporal decay half-lives to ensure older, highly similar memories do not mathematically outrank newer, relevant truths. The design philosophy here is pragmatic. The system keeps standard text files as the editable, human-auditable source of truth, and treats vectors merely as a derived search capability. Oracle's engineering analysis clearly establishes the exact boundaries where file systems fail and standard databases must take over. The first breaking point occurs within the document itself. Overly large files create unbounded instruction drift and intense context budget pressure, eventually reducing the model's adherence to its own rules. The second breaking point is the catastrophic failure of concurrency. When multiple distinct entities attempt to write to the same underlying file simultaneously, data corrupts. The moment an architecture moves from a single agent to a multi-agent system, database guarantees regarding atomicity and isolation become mandatory. Atomicity ensures a transaction entirely succeeds or entirely fails, while isolation guarantees concurrent transactions do not interfere with each other. The final breaking point here is scale. Keyword search completely degrades on paraphrased concepts and synonyms, making managed vector infrastructure a necessity for massive knowledge bases. Databases solve human collaboration and multi-threading problems. They do not solve foundational single-agent memory problems. The equilibrium architecture for modern AI agents is straightforward. Default to files as primary interface, rigorously offload large artifacts to disk, and index those files locally. The escalation rule is strict. Only migrate your substrate to a dedicated database when concurrent access and shared state force the transition. If you're building agentic workflows, hit subscribe to the Bearded AI Guy and drop a comment below outlining the context architecture you are currently testing. An autonomous agent requires a functioning text editor long before it requires a $50 million data layer.